Okay, let's continue. And we have, as mentioned, one additional short bit of lecture material. It's kind of just essential stuff you need to know to help you out with the exercise for this week. And so we'll cover that. And then we can talk about the exercise. So let me just, again, put this on here. So we're going to talk about, since we'll be using the heat transfer equation to look at advection this week in the exercise, we're going to have to talk a little bit about some things that advect heat. Two of the most common processes in which heat is advected or moved within the crust of the earth are erosion and sedimentation. And of course, then we're going to talk about how these relate to heat transfer, just to give you some idea what to expect when you look at the outputs from the code that you'll be using in the exercise for this week. We'll actually come back to this same equation that we're using in this week's exercise in another exercise, probably in week 6, but we'll come back to that and learn a bit more. So we'll just kind of get a taste of the topic in the slides here and in this week's exercise. So there's two things I want to point out here. One is about some terminology. This is mostly just to make sure that you're clear and maybe not confused about what we're referring to, and then talk about heat transfer as a result of either erosion or sedimentation, just looking at things in one dimension, so only considering how heat is transferred vertically. So we're not looking at like fold and thrust belts or someplace where there's a lot of horizontal movement of material or heat. The reason for doing this is that if we look at thermal chronometers, as we will in the coming weeks of the course, there's essentially two things that they can record. The main one is cooling. So as you saw, for instance, with the Dodson's equation last week, and we had these closure temperatures, the temperatures that you're calculating for the closure temperature is something that is going to be able to be interpreted as the time since the rock was at that effective closure temperature. And normally these rock samples are collected at the surface. So we're looking at how long it was since it cooled down below the effective closure temperature. So that's the thing. It's essentially measured by a thermal chronometer, and the way that the ages can be interpreted in the simplest way. Depending on the tectonic setting, most of the time it's exhumation as a process that leads to that cooling. So it's erosion of material at the Earth's surface that brings rocks from deep below the Earth's surface up toward the surface. And as they travel from somewhere deeper in the Earth to the surface, they cool down. I think it's no great leap to recognize it's hotter in the inside of the Earth than it is at the surface. And so if some rock parcel is to move from somewhere inside the crust up to the surface, it's going to be cooling for the most part in its pathway up toward the surface. So exhumation is the process essentially of just removing the material above the rock to allow it to move up toward the Earth's surface. Erosion is often the process that's removing that material. But there's also tectonic exhumation, like if a normal fault slips, the slip of the normal fault can actually bring rocks up closer to the surface just by tectonics. So it's not exclusive to erosion, but often erosion is involved in some way or another. So that's essentially what our thermal chronometers record. And there's a few definitions that are given here. I'm not going to spend any time really on this slide. It's just in here for your own reference if you're confused about some of these terms. Exhumation, denudation is another term that's often used, and then erosion. So you can find some definitions here, but I'm not going to talk about those much. What I want to focus on instead is the kind of concept about what advection or sort of what the advection as a result of exhumation does to temperatures in the crust. So when we have exhumation active as a process, when we're moving rocks up toward the surface, this upward motion advects heat, means you have basically warm material moving up closer toward the surface, and the surface rock is being eroded and transported away, for instance, by a river or glacier. And this upward movement of the mass is making the temperatures higher because the rock that was down here at some greater depth was hotter than it was or would be if it were closer to the surface. And if it moves up toward the surface fast enough, it's going to stay hot before it can cool down from heat conduction, and that will increase the temperatures in the crust. That's essentially how things are working, and that will do things like increase the geothermal gradient as one example. In terms of the rates at which this process becomes important, it's usually for velocities of greater than 0.1 millimeters per year. This is the same thing as 0.1 kilometers per million years. So just to give you a kind of reference there, it'd be about 100 meters per million years. If there's more than that amount of exhumation, then you would expect that the advection process is going to be heating up the rocks in the crust, and that will then have an impact on your crustal temperatures. In a place like we have here in a stable shield setting, the advection velocities are probably several orders of magnitude lower than 0.1 kilometers per million years, which means advection is not really a process we need to worry about here as a heat transfer process when we look at the lithosphere in Finland as an example. However, there are sometimes groundwater circulation and other things that can influence this. Perhaps the most significant being past climate conditions, which can influence temperatures down to maybe 1 or 2 kilometers below the Earth's surface. So there are things that can affect temperatures, but advection is not so important in a stable shield setting. All right, so we saw our one-dimensional steady state advection diffusion equation in the previous kind of derivation that was shown on the course page. That will be up again, as mentioned, sometime this evening. That derivation is for the steady state case where temperature is not changing with time. Here we have an equivalent, or it's a similar equation, but now solved in the case where time matters. As you can see, things get a little bit more complicated when we consider time into this equation, and you end up with some kind of nasty looking thing like this that you will also get to explore in this week's exercise. Now, there's going to be maybe some need to discuss how to approach this kind of equation, but I can say in spite of looking nasty, it's easier to deal with than Dodson's equation was last week. There's no iteration or anything like that. We have an error function or complementary error function here. That's something we can use from the SciPy library, so there's no worries about dealing with that too much. And I'll tell you that this is all in all not too bad. The worst thing you have to worry about with this equation is just balancing the parentheses and making sure that everything is actually working correctly in terms of the things that should be added together before being multiplied by something are wrapped in parentheses to make sure that that does happen. So we'll deal with this guy in the exercise, but don't panic. It's not nearly as bad as it looks. And in fact, it's probably better that you write your own little function with this than what's happened in years past, which is I give you a code with this temperature equation in it, and you probably have no idea how it works because you didn't actually write the code up yourself. So how does this equation work in terms of what it does in the concept? Well, this is a one-dimensional heat transfer equation, including advection and diffusion. The only difference from the steady state case really is that we are now depending on time. And there's a big G here instead of a little g. The big G in this case is the initial temperature gradient at the start. So at time 0, the initial temperature gradient would be some constant change in temperature with depth. So let's say it gets 20 degrees C hotter for every 1 kilometer you go deeper into the model. That's what the big G is here. And then we start out with that condition and then see how over time things are changing. Very similar to how the other equation was working in terms of the concept, although you'll see in the exercise, the results that you get are a little bit different. So how does it work? Well, let's envision a situation like the one that's shown here on the figure on the right. This is for erosion the Earth's surface at a millimeter per year, 1 kilometer per million years. We've got depth of 10 kilometers shown here, and then temperature is on the horizontal axis here. At the beginning, you can see the temperature goes up to 0 at the surface, and at the start, it went down to 250 degrees at 10 kilometers depth, which means temperature was increasing 25 degrees per kilometer. Over time, as a result of this erosion and the advection of heat up toward the Earth's surface, you can see temperatures are increasing by, this is every 5 million years that you have a line drawn here, so that after 15 million years, the temperature is quite a bit hotter than it was at the beginning over this 10 kilometer range of depths. If we were to flip things around and do just the opposite, and instead of eroding material, so moving things up toward the surface, deposit sediment so that the surface is moving down with time, then you get just the opposite effect. Things are cooling down over time. So as you have sediment deposition at a millimeter per year, you see from the initial temperature that our temperatures are actually getting cooler and cooler with time as the sediment is being pushed into some basin and cooling the rocks around down. So just to kind of think about this in one other way, we can also talk about how the temperature gradient changes. This is not maybe so closely linked to the exercise for this week, so it's not terribly important, but we can see it in the illustration here that if we take this model at the starting time and we go down to 2 kilometers depth, if we followed this line all the way down to the bottom, you'd see that the temperature is 50 degrees hotter at 2 kilometers than it was at the surface. That's the 25 degrees C per kilometer temperature gradient that was imposed as a starting place for calculating the temperatures with this equation. After 15 million years, if we go to the same depth, we would be at this red star over here for our temperature. And now if you follow that down to the bottom, you see the temperature is about 100 degrees at 2 kilometers depth. Our temperature gradient has gone up by a factor of 2. So now it's 50 degrees C per kilometer for the temperature gradient after 15 million years of erosion at 1 millimeter per year. So that's how it's affecting our temperature gradient. You can see just because the temperature increases at the same depth, that means the temperature gradient will go up. So we can look at this in a few different ways. I'm not really going to worry too much about these figures because if you're interested, I'd say you can have a look at them yourself. But this essentially is just saying that for however long erosion's going on and whatever the rate of erosion is, whether it's 0.01 millimeters per year, 0.1, 1 millimeter per year, or 10 millimeters per year, this is just showing you how the temperature gradient would change and how it would change after a certain amount of erosion. So as you can imagine, the longer the erosion process is taking place, the more the temperature would be affected in the crust. If it happens only for a very short time, then nothing will really happen. Temperatures won't change in any significant way. But I think that's all I'll say about that. If you're curious, you can look through the figures and let me know if you have questions. But we don't deal with this concept so much in the exercise this week, so I'll just leave these here as a kind of a reference for you. So just to recap, erosion and sedimentation both will affect crustal temperatures because they advect heat. The erosion tends to move mass up toward the surface. You basically remove the rocks above by erosion processes, and then the rock underneath it is displaced upward, and that heats the crust. Sedimentation has just the opposite effect. The rate at which you erode or deposit sediment and the duration, so how long that process is active, both will affect how much the temperatures are changing. So very slow rate for a short period of time, not going to affect the temperatures. Very fast rate for a very long time will have a big effect on your temperatures in the crust. And if you remember nothing else, the general expectation is that exhumation heats the crust and sedimentation cools the crust. Now, obviously caveats apply, but that's the simple thing to try to keep in mind. And I think that's it for the kind of intro intro stuff. Do you have any questions at this point? So I'm not seeing any questions at the moment. And if there's anything that comes up and comes to mind, you can, of course, take a look over to the chat in Zoom here and put a question in there. That would be great. I'm going to go here now to exercise number 4. And I will once again make this available on the regular course page in just a moment. Once we finish up class, this is actually looking like it's still the old exercise. It is. So the link is not yet updated, but no worries. We'll go here and take a look at exercise number 4. Okay, so as you can imagine, we're dealing with advection and diffusion in this week's exercise, and we're talking about heat. And you can find the basic information about the exercise here, links to the lesson materials and hints and all of that stuff. And it's due next week on Monday as usual. If we take a look at the problems we have themselves, there's a few things here. One, there is a problem number 0 this time. It's a midterm course feedback. It is not worth any points, but I would be very happy if you would go here to the feedback link once it's made available and just take a couple minutes and give feedback about how things are going in the course so far. There's still time to improve and make sure that what we're doing in the course is helping with your learning. So your feedback is really helpful for me, and I would really appreciate you taking a couple minutes to provide that feedback. So that's the first thing in the exercise. Problem number 1 is about steady state advection and diffusion. So just start out with a couple definitions here just to remind you that the steady state means that the temperature is not changing with time. So it's kind of like the temperature after an infinite amount of time, or in which case, like if you add more time, nothing would happen to the temperatures you have calculated. This is in contrast to the time-dependent case where the temperature is changing as a function of time. So that's just our starting place. We've already been down and seen this equation. With this equation that we saw already in the derivation part of the introduction to the advection diffusion equation for the course, with that, we basically have something that we can explore this effects of advection and diffusion without considering time. So you see that the temperature here, T, is only a function of depth. That's the first equation you're going to convert into a function. So just like the week before, you're going to have the same opportunity to copy over your exercise number 3 functions file and then run these tests that should work if everything is working properly from the previous weeks for your functions. If you're having problems with your functions, this is a good opportunity to check with us and get some help to make sure that your code is doing what it should be doing. Once you've just done the kind of copying and testing things, then you're going to make a function for calculating the steady state temperature. It's called steady state temp. Should be hopefully a fairly obvious name. And if we look back at our equation, we have to give a couple things in order to calculate a temperature. We need to give a gradient at the surface. We need to give a thermal diffusivity. We need to give a velocity, and we need to give a depth or range of depths at which we're calculating the temperature. So you can see those are the parameters that you're supposed to then use in your function that you're creating. So you'll define that in this script file. And then here you have some tests you can run to see if your steady state temp function is working as it should be. There's 3 tests, I guess, here. If you pass all of those, you could feel reasonably good that your function's working properly and move on to part 2. So there you'll use your function to calculate a geotherm. That's just a fancy way of saying the change in temperature with depth. So we'll calculate geotherm 1 with the input values that are listed here. So you'll just do the calculation. Again, you've got a test cell to see if everything worked properly. Then you make a plot of that first steady state geotherm. And then you go back and do the same thing again, but you calculate a new geotherm for a different advection velocity. So now we erode twice as fast, and we see how the temperatures change. So that will be it then for problem number 1. So relatively, I hope relatively straightforward in terms of what to do and how to get to having a couple plots, a new function, and things like that. Problem number 2 is very much in the same kind of template as problem number 1, but now we're going to deal with time. And as you saw, when we deal with time, we get a little bit nastier equation we have to handle. It's not so bad, but it does take a little bit of extra effort to get this one working properly. We can talk a little bit about strategies for handling this thing. But the basic idea will be, again, to make a new function in which you calculate now a temperature as a function of both the depth and time. So you'll first do this creation of your time-dependent geotherm function called transient temp. Transient's just a word to mean it's changing with time. I couldn't really think of a shorter way. I could have gone time-dependent temp, but that seemed kind of clumsy to type in. So transient temp will be the word that we're using for our function. And then here we have an initial gradient of diffusivity, velocity, depth, and then time. So just as a reminder, the initial gradient in this case is the temperature gradient from the top to the bottom of the model at the start, so at time 0. And then time here would be given in millions of years, and that would be, then 5 million years later, where you would calculate, for instance, what the temperature would be. One thing to note both about this function and the function in problem number 1 is that you can use the units that are given here. You do not need to worry about converting units from kilometers to meters or from millions of years to seconds. Those are the SI units, but these equations will work properly with kilometers and millions of years canceling each other out so that you get a temperature out of there. So you don't need to worry in this case about doing the unit conversion, which was something that had to be done, I think, last week when we were dealing with Dodson's equations. A little bit easier, I suppose. You'll see there is an ERF-C function in this equation here. You can see the complementary error function listed twice. You can use the complementary error function straight out of SciPy's special library. So you can just do this from scipy.special, import ERF-C, and then you'll be able to use that in your function to calculate what the temperature should be. So once you've created the function, of course, like before, there's a couple tests to see whether your function's working properly. Then you calculate another geotherm. This is geotherm 3. After 10 million years, we calculate what the temperature would be in geotherm 3. And then, of course, a test to see if that worked. Make another plot where you just plot up this geotherm 3. Do the same thing like we did in problem number 1. So calculate another geotherm and also plot it. So you'll plot geotherms 3 and geotherm 4 together to see how they compare to one another. And then finally, you make one last plot where you plot the first 2 steady state geotherms along with the last 2 time-dependent geotherms. And you look at how all 4 of them compare to one another. And you'll have an opportunity to then reflect on what you have seen in the optional reflection questions. So they are optional. They're not contributing to your grade in any way, but it is useful maybe to take a moment to try to answer these questions just to assess what you've understood from the exercise for this week. So that's exercise number 4. It's, I think, manageable in terms of how much you have to do. I've left a decent amount of time in terms of not trying to give you too many things to keep you too busy to have time to get this bigger equation working properly in your code. It may take a bit of testing to get the parentheses all balanced and things like that. Do you have any questions at this stage? So what I'm thinking I'll do is I can maybe stop the recording, and then I will try to make this exercise page visible so that you can create your copy of the exercise if you'd like and start looking through it. And then otherwise, I'll stay here in Zoom until around 4 o'clock, and I could be here to answer questions if you have questions or to discuss anything. Actually, one thing I did want to discuss now that I'm thinking about it is we do have one function we need to use both for problem 1 and problem 2. Let's just take a look at problem 1 because the equation's a little bit easier to look at. Here it is. So you'll see there's a 1 minus e to the something in this equation. There's also several of them in equation number 2. That's an exponential function. So if we were in NumPy, or if we were using NumPy, and let's put this as a code cell. If we import NumPy as NP, that's the normal way to bring in NumPy. You can take some value where you want to calculate what the exponential is, and it's simply np.exp of whatever that value is. So if we take exp of 1, we get 2.71 blah, blah, blah. That's the value of e. If we do e to the 0, of course, we get 1 back. So it's np.exp in order to calculate the exponential value of something. So you'll need to use that here, for example, where you take e to the minus vz times z over kappa. So you'll use np.exp for doing that calculation. I think otherwise you'll have seen basically everything you would need in terms of Python skills to deal with this problem in exercise number 4. Okay, so if there aren't any urgent questions at the moment, like I said, I'll turn the recording off now, and I will get the exercise so that you can access it, and you can then get started with that if you'd like. Otherwise, I'll be here and can answer questions.